Hello guys, so we're gonna continue our discussion about negative clipping. I'm gonna, analyze this circuit in another more deep way. What we're gonna do, we gonna divide the analysis in two steps. The first step is to check the input in the positive half cycle. This cycle here, this is the positive half cycle. Then check the behavior of the circuit, when the diode is on or off in the negative half cycle. Okay, so let's start by the positive half cycle. So in the positive half cycle, the positive is here and the negative is here. And that means that since this is an EC source, that means that the voltage of that node is greater than the voltage of that node by these values here, whatever the value. At t equal to 0 here, at the beginning, they have the same voltage. That's why the voltage difference is 0. Okay. Then, for example, here, if it's 1, for example, or whatever, then that means the voltage of the positive polarity is greater than the voltage of the negative polarity of the ground here in that case by 1, and so on until we reach here. Then here the voltage of the positive is greater than the voltage of the negative by Vm, and so on. So basically, this input can be changed into a battery like this, although its value is changing all the time. And we can represent the circuit in that way. Okay. Or what I want to do now is to know, when the diode, if the diode is forward or reverse. That's what I'm gonna do right now. This is V input, and this is VB. And remember now, V input, this node in the positive half cycle always greater than this node in value, or the input is positive. Okay, as we see here. Then I'm gonna move VB like what we learned last time into that branch here. So if we do that, remember it is series, so we can do that. So it's gonna move in that way. Here is the ground. Here is V input. So this is V input. This is VB. And look now, both are in the same direction. And VB here is greater than 0. I mean, assume, for example, that VB is equal to 2, for example, or 4, whatever, 4, and V maximum equal to 10. Just an example, So this is minus 10 here, and this is 10. So look at this situation now. V input is all the time positive, okay? And VB is also positive, and both have the same polarity. So this can be reduced to the following circuit. And this will be Vn plus VB. And this value here is always greater than 0. Always. So now we can, see that the diode will be all the time during the positive half cycle reverse, because its N is closer to the positive terminal, its B is closer to the negative terminal. It's actually, connected to the negative terminal. So it's reverse. Or you can say this battery wanna push current out of the positive terminal, and the currents cannot move from N to B in the diodes. So diode is reverse. So this guy here is reversed. So it's off. So during the whole positive half cycle, the diode was off. So in the positive half cycle, the diode is always off. So if the diode is off, then the current all the time is equal to 0. So VR, which is the voltage of the resistor, which is IR, I times R, is equal to 0 as well. So we can say that from Kirchhoff voltage law here, when V input equal to VR plus VO, so this is V input, this is VR, and here is VO in that direction, and as you see, VO plus VR equal to V input. So we can say here, since VR is equal to 0, that VO is equal to Vn. So based on that way, this new type of analysis, we discovered that during the whole positive half cycle, the diode was off, and the voltage of the resistor will be 0, then VO will be just equal to V input. Okay? Just by Kirchhoff. That's good. Now let's do the negative half cycle. So let's do it in another color. Red, for example. What it is mean that the voltage, for example, is minus 10. This is circuit theory now, okay? So when we say in the negative half cycle that the V input is minus 10, that means that this node, let's call it A, is greater than B, which is the negative terminal, by minus 10. Or in another word, we can say that B is greater than A by 10. Okay. When you draw the input like this, you assume that the direction of the input voltage is the same all the time. And what does that mean? That means that you assume all the time that this is the positive and this is the negative. You assume all the time that A must be greater than B. Okay? So in the bottom of cycle, you know, this is understandable. We can say, for example, here at 10, that A is greater than B by 10. In the negative half cycle, since B is a greater now, we must give the voltage negative sign. So we can say still that VA is greater than VB, the negative terminal, by minus 10. When we say this is greater than this by minus, that means it is actually the opposite. Okay. So, you know, to have a piece in our mind, okay, this way of analysis will do something, you know, a little bit counterintuitive. We're gonna go back to the original definition, you know, or the fact, we can say, that in the negative half cycle, the fact is B is greater than A. So what we're gonna do, we're gonna change the polarity. So we're gonna consider input in that way. So let me erase this. Oh, we'll keep it. So we're gonna keep what we have in the positive. But for the negative now, for the negative half cycle, I'm gonna draw again with red, but I'm gonna flip what we have here. So as a negative half cycle, I'm gonna consider A negative terminal of the V input. Remember, V input is AC wave or AC signal, and B is the positive, and the direction will be in that way, and that's very important because you're gonna drive now Kirchhoff voltage law based on that new direction, and this will change many things. That's very good. That's very good. So based on that, since you consider now the polarity is flipped in the negative half cycle, you must also flip the voltage difference. So let me do that in red. So we're gonna now consider the red input, the red signal in the negative half cycle. And this will be 10. Remember, in the positive half cycle, you are considering A and B like this. So this is A, the input is like this. This is A, this is B, and this is positive, this is negative, this is negative. Now in the negative half cycle, if you consider A, if you consider the same assumption, A, B, and positive, negative, then you have this black or negative values. But if you consider the red, you will have something like this. You will have again battery, which is a changing in voltage, of course, A, B again, but negative and positive. But you consider the values now are positive. Now, when we say the input is 10 in the what was previously the negative half cycle, now that means B is greater than A by 10. If you want to consider the black one, you say that A is greater than B by minus 10. And you should consider the opposite way in the direction of the voltage. Here, the direction is in that way. If you consider the other one, you consider the voltage in that way. Basically, you either flip the voltage sign or flip the voltage direction, the arrow or the value. You go with either this or this. Of course, in all your circuits in your life, you're gonna go with the positive and negative, and you're gonna check, stick with the same polarity each time, either in the positive or the negative cycle. But for this type of question, I found it very, very easy or easier than the other one. It will make you understand more and visualize more the real situation of the diode, either it's forward or reverse. Okay. So let's continue now with the red. Now we have this input, which is the red now. And this is the polarity of the input, negative, positive. And the value is still positive, like the first half cycle. So in the first half cycle, positive, negative, A, B, and the values are positive, like what's given. In the next half cycle now, we have AB still, but negative positive. And the direction is from A to B right now. And the values are positive. Okay, so let's draw that now. Let's draw a circuit like what we did here in red. So now we have this situation. We have our red. So let's change it back to red here. So we have this situation now. We have the diode is like this. We have VB, which is positive voltage. We have here the resistor. Then we have here another battery, which has voltage value, positive voltage values, and here is the ground. This is now V input. Call it V input dash. So this is V input dash, which is just V input, but with negative polarity, minus V input basically, minus the original input. Okay, and this battery is giving you positive voltage, like for example 10, 5. And this is again positive. Now turn VB to the location of Vn. So we're gonna have something like this. So VB is in the other way. I'm very sorry. So VB is in the other way. Negative, positive. So when we move it, it will be like this. And don't forget the resistor. So this is VB, and this is VM dash. This is in that way, and this is in that way. So now they are opposite. They are not like this situation, which both was in the same direction. Now we have two batteries opposite to each other. Now I'm gonna give you examples to see if they are just examples, if they are forward or reverse. So let's have examples on a side here. Side notes. Let's assume that Vn dash is 1 and Vb is 2. So you have this situation, 1 and 2, and here is the diode. This is forward or reverse. Let's check. So these two will give you a battery for going in that way, like this. And the value is 1. This is basically reverse. And the diode is off. Okay. Let's have another example. How about Vn dash is 2 or 3, and Vb is 2, still 2. So we have this situation. This is 2, this is 3 now. Oh, the ground is in between. But we can reduce that to a battery, but in that direction. And also 1. So look, the battery here is in that direction, the battery here is in that direction. This is positive, negative, this is negative, positive. Now the diode is forward. This is forward. And since the battery is greater than 0.7, it's 1, then that means it's enough to give the diode 0.7, and the rest will go to the resistor, which is 0.3. And the diode will be on. So here the diode is on. And you can prove it. You can just solve this, assume on, or assume off, for example. And you're gonna see that there is something, not right, and it must be on. Okay? And you can play this game, you can assume whatever value here and whatever value here and find, what value will make the diode is on. Or you can make the game that we learned, which is finding the input minimum, which is the general, solution. Okay? So in that case here, D is forward with one of them. Basically, it's a forward with V input dash. Look, N is closer to the minus, and B is closer to the positive. So D is forward with Vn dash. At the same time, D is reverse with VB. So they counteract each other. In the first half cycle here, both D was reverse with both. So the N was closer to the positive of both, and I'm sorry, and the B is closer to the negative of both. Here, no. The diode here is N is closer to the negative of B, but Vn dash, but positive of VB. And the opposite was the B side. Okay. So basically here we need Vn should be greater than or equal to VB in order to make, the overall situation forward. And to make the diode on, it should also be greater than, not just the VB, but VB plus 0.7. And we'll calculate it. So we should calculate V input minimum to turn, or V input dash minimum now because we call it V input dash, to turn the diode on. Let's do that. At Vn dash equal to Vn dash minimum, Vd will be 0.7 and ID equal to 0. Remember, guys, we said that when it start on, start from this bottom, point in the characteristic in which the current is 0, but Vd is equal to 0.7. Once V input exceeds V input dash, the diode voltage will be constant at 0.7, but the current will be greater than 0 based on the circuit condition, the amount of resistors, the value of the input and so on. So let's put the circuit here in that condition. So this guy will have 0.7 in that direction. Here a resistor, and here is our Vn dash minimum, and here is Vb. Okay. So remember the current is 0, so the current here is 0. So let's make Kirchhoff now. So from Kirchhoff we can see, so stick for the resistor, stick with the original direction. So we assumed that the direction is in that way, stick to that direction. For the resistor, stick to one direction, either in the positive or the negative. So let's do Kirchhoff now, KVL. I'm gonna find that Vn dash minimum minus Vb minus 0.7 plus Vr equal to 0. Remember, Vr is 0 because I is 0 and I times R is 0. So Vn dash minimum is equal to Vb Vb plus 0.7. So in the next half cycle, I'm not saying negative now because we have flipped the sign from negative to positive. When V input dash is less than Vb plus 0.7, then the diode will be off. When the input exceeds that value, the diode will be on. So let's explore both conditions. So number one, when V input dash less than Vn dash minimum, the diode is off, I equal to 0. And now return to the original circuit because we want to calculate V output, which is the voltage of the diode and Vb. So this is the original circuit here, and here is VO. And here is V input, or V input dash, as we call it. And here is the ground. So when Vn dash is less than Vn dash minimum, that of I is 0, so Vr is 0. And Vr is in that way. If we do Kirchhoff, Vn dash plus VO plus Vr equal to 0. So VO is equal to minus Vn dash. Number two, when Vn dash is greater than Vn dash minimum, the diode will be on. So Vd is equal to 0.7. Now we can calculate V output. V output will be constant. V output, remember, is equal to, let's do it. This is Vd, This is VB. So it's equal to minus VD minus VB. So it's minus 0.7 minus VB. Of course, we have numbers for VB and VD, but I like to leave it in terms of VB, assuming that VB is greater than 0. Okay. If we wanted to compensate, it's really easy. VB is 4. We assumed it's 4. So it will be minus 4.7. So there will be clipping at minus 4.7. So VO is constant now, equal to minus 4.7. How about VR from Kirchhoff? Let's check Kirchhoff here. So we have the same equation basically, that Vn dash plus VO plus VR equal to 0. So VR equal to Vn dash or minus Vn dash minus VO. So equal to minus Vn dash plus 0.7 plus VB. Or we can say minus Vn dash plus 4.7 or minus 4.7, which will be 4.7. Okay. Good. So now let's draw all of that. So we have all the equation we need. It's just the matter of plotting now. So let's start drawing by the positive half cycle because it's easier. The positive half cycle, we have one situation. The diode is all the time off, VR is 0, and V output is equal to V input. Okay, let's draw VD or V output in blue and VO in red or green. Okay, so let's start by VD. So VD is equal to, in the positive half cycle, VD is equal to V input. Whatever the V input is, V out is equal to V input. So when V input is 0, V output is 0. When V input, for example, is 1, V output is 1. When V input is V maximum, which is 10, V output is V maximum. And again, so it will be exactly the input. So just copy and paste. Copy and paste that signal here. Because we discovered that during the positive half cycle, V out is equal to V input. And again, during the positive half cycle, VR is 0. So let's go with green. So this is the positive half cycle. Just draw 0 like this. Good. Now, the next cycle, I will not call it negative half cycle, or it's negative half cycle if you assume all the time that A is positive and B is negative. But we're going to stick with the red one here. So we can say it in the second half cycle, in which A is negative and B is positive, and we are dealing now with V in dash, is the red one. Let's check the equations. We have two situations. The first one is when Vn dash is less than V input dash minimum. And what is V input dash minimum? V input dash minimum is VB plus 0.7, which is basically VB is 4, 0.7 is 0.7, so 4.7. So we need, a line at 4.7 to divide. So let's assume, for example, this is the 4.7. Let's assume, for example, this is the 4. This is V input minimum or V input dash minimum. I'm gonna go like this. Okay. I'm gonna make straight lines. And let's now plot what we have. We said that when the input dash minimum is less than the input dash, when the input dash is less than the input dash minimum, VR is 0 and the output is equal to minus the input. So let's start by VR because it's easier. VR equal to 0. So VR equal to 0. Let's check this area. So in that area here, from that point to that point, the input dash is less than the input dash minimum. And again, from that point to that point, the input dash is less than the input dash minimum. Remember, this is the input dash minimum. This is the 4.7. So all these values are less than the input dash minimum. So from here to here, we have 0. And from here to here, we have still 0. How about VO? VO is equal to minus VM. So let's see how we're going to do that. So we go to blue now. So what you're going to do basically is it's a flipping copy and paste. I mean, a flipped copy and paste. So basically, 0 here, this will be minus 0. Of course, it's 0. This is, for example, minus 1. I'm sorry, this is positive 1. This will be minus 1. This is the input dash minimum 4.7. This will be minus 4.7. So basically, take this one here and flip it. So it's going to be like this. Where this is basically minus the input dash minimum. This is basically minus 4.7 because when the input dash is 4.7, this will be minus 4.7. And again, do the same in that region from here to here, from here to here. Again, when the input is the input dash minimum, which is 4.7, this will be minus 4.7. And again, whatever you have here, you will have its negative here. Okay, until you reach 0, 0 minus 0 is just 0. Okay, so this is basically, you know, the input or the output, I'm sorry, when the input dash is less than the input dash minimum. Now, how about the other half or the, you know, this period here in which the input dash minimum is greater than, or the input dash is greater than the input dash minimum. Basically, in that case, the output will be constant, minus 4.7, which is minus the input minimum, right? So the input dash minimum. This is basically minus the input dash minimum. Remember, this is V input dash minimum. It was VB plus 0.7. This is minus V minus 0.7. Let's do that very quick. So remember, the last 2 points that we reached into here was minus V input dash minimum, minus 4.7. So basically, you just connect these together. And that's basically VO. How about VR? VR is minus V input dash plus 4.7. So whatever the input dash is from this point to this point, you multiply it by minus 1, then add 4.7. I'm gonna start with this hip here, with these 3 points. This point, the start, the end, and the middle. In the start here, the input dash is equal to 4.7. So I'm gonna multiply it by minus, so it will be minus 4.7. Then add 4.7, it will be 0. So this, let's change it to green. This will be 0, which is basically the last point that we reached from this period. And in the middle, the input is 10 or V maximum. Okay, so you multiply it by minus, so it will be minus 10 or minus VM. Then we add 4.7. So it will be minus 10 plus 4.7. It will be totally minus 5.3. So it's minus. So It is something in minus here. Minus Vmax plus 4.7, which is minus 5.3. And you should do the same with these values as well. So what's gonna happen is that it will give you the same triangle from that point to that point. So basically, this triangle here is exactly flipped here. Okay, this is VR and this is VO. And again, if you add them together using Kirchhoff, you're gonna get, you know, this input again. So now I'm talking about the, you know, the black one, or even with the red one. So let's look here. From the original polarity, you have here V input in that way, and here is VR and here is VO. So V input equal to VR plus VO. So if you take this green and just put it here, it will give you the same negative half cycle here. If you want to go with the blue, with the red one, you go with this equation here. Which is V input dash plus VO plus VR equal to 0. Or V input dash is equal to minus VR minus VO. So if you multiply this by minus, it will be something positive like this. And if you multiply this by minus, it will be positive like this. And if you add this triangle to this shape here, it will give you exactly V input dash. Okay, guys, so this is basically the negative clipping. In the next video, I'm gonna explore another circuit in which we're gonna clip from both sides. So till this moment, you either clip in the positive half cycle or you clip here in the negative half cycle, but you don't have both. So in the next two videos, we're gonna explore two other circuits, two versions basically of the same circuit that do the clipping in both positive and the negative half cycle. Okay, so stay tuned for the next videos. Bye-bye.